In medicine, you're constantly looking at numbers, but sometimes a few of those numbers can mean absolutely everything. Today, we're going to crack the code on one of the most critical and, yeah, sometimes confusing lab results out there. Let's jump right in. So you see this on a patient's chart, an arterial blood gas, or an ABG. At first glance, it might just look like a jumble of numbers, but what it really is a clinical puzzle, a snapshot of what's happening inside your patient's body. And today, we're going to learn exactly how to solve it. So how do we do it? Well, we have a roadmap. Think of this as your detective's handbook. These 7 steps are going to take us from total confusion to complete clarity, breaking down the problem piece by piece until we know exactly what's going on. Let's start the investigation. All right, like any good detective story, you start with the most obvious clues. For us, that means we need to answer 2 really basic questions. First, is there actually a problem? And second, where is that problem coming from? Step 1, thankfully, is the easiest one. You just look at the pH. A normal pH is between 7.35 and 7.45. So if it's below 7.35, the blood is too acidic. We call that acidosis. And if it's above 7.45, it's too alkaline, or alkalosis. That's it. We now know if there's a problem and what kind of problem it is. Okay, so we found our first big clue. We have either an acidosis or an alkalosis. The very next question any good detective asks is, where did it come from? What's the source? Is this a problem with the lungs, a respiratory issue? Or is it coming from somewhere else in the body's chemistry, a metabolic issue? This is a really crucial step. And this slide tells us exactly how to find that source. We're looking at 2 key players here. PCO2, which is carbon dioxide, controlled by the lungs, and HCO3, which is bicarbonate, managed by the kidneys. If the PCO2 level explains the weird pH, boom, you've got a respiratory problem. If the bicarbonate is the one that's off, it's metabolic. This is the first major fork in the road of our investigation. Okay, so let's say our clues pointed us down that respiratory path. Now our investigation has to get a little more specific. We need to figure out the timing of this thing and see how the body's trying to fight back. So we know it's a lung problem, but the next question is this something that just happens suddenly, what we call acute, or has this been going on for a while, making it chronic? Knowing the difference is a huge piece of the puzzle. So how do we figure it out?
We actually use a pretty neat formula. Now, don't get hung up on the math here, just focus on the big idea. This formula basically predicts what the pH should be if the problem is brand new. So we do that calculation and then we compare it to our patient's actual pH. If they match up, it's an acute problem. But if the patient's real pH is a bit closer to normal, that's a huge clue that the body has had time to start fixing things, which tells us it's probably chronic.
The body is pretty smart. When the lungs are causing a problem, the kidneys try to jump in and save the day. This is called renal compensation. The kidneys will start adjusting bicarbonate levels to try and pull that pH back to normal. Our job, as detectives, is to figure out if that response is strong enough for the situation. And guess what? We have a set of simple rules to guide us here, too. This table shows us exactly how much we expect the bicarbonate to change for any given respiratory problem. So we check our patient's labs against this chart. If it matches, great, the kidneys are doing their job. But if it doesn't, well, that's a big flashing sign that there might be a second hidden problem we need to uncover. Okay, hit the rewind button. What if back in step 2, our clues didn't point to the lungs? What if they pointed to a metabolic cause? Well, now we head down a different, but just as systematic investigative path. So just like the kidneys help out with lung problems, the lungs step up to help with metabolic ones. It's teamwork. The body can change how fast or slow you breathe to either blow off CO2 or hang on to it, all in an effort to get the pH back to where it should be. So our next job is to check, are the lungs compensating like they're supposed to? And here's how we can predict what the lungs should be doing. For metabolic acidosis, there's a really famous equation called Winter's formula that calculates the expected PCO2. For alkalosis, it's a different rule of thumb. This step tells us if the lungs are pulling their own weight in this fight to restore balance. All right, now if we've confirmed we have a metabolic acidosis, we get to pull out a really special tool from our detective kit, the anion gap. Now, this isn't something the lab measures directly, it's a value we calculate, and it is incredibly helpful for narrowing down the possible causes of the problem. It's a huge clue. And the calculation itself couldn't be more straightforward. As you can see, you just take the sodium and subtract the chloride and bicarbonate from it. This simple little formula gives us that powerful clue, the anion gap. Now, the magic number you need to remember here is 12. If your calculated anion gap is greater than 12, we call that a high anion gap metabolic acidosis. And what that does is it immediately points our investigation towards a very specific list of suspects, things like lactate or ketones that are adding extra unmeasured acid into the blood. Okay, this is it, our final and most advanced step. This is the move that takes you from being a good detective to a truly great one. We're going to see if the change in that anion gap we just calculated matches the change in the bicarbonate. It sounds complicated, but this little comparison can reveal a second hidden problem that's happening at the exact same time. So here's what we do. We compare how much the anion gap went up to how much the bicarbonate went down. In a simple, straightforward case, those two changes should be about equal, but if the gap has increased more than the bicarbonate dropped, it's a sign that there's also a metabolic alkalosis hiding in there. And if the gap has increased less than the bicarbonate dropped, it tells us there's another kind of acidosis present. This is how we find those really complex mixed disorders. And just like that, we've done it. By following these 7 steps, we went from a totally confusing set of numbers to a really precise, detailed diagnosis. The case is officially solved. So let's run through that checklist one last time. You always start with your first clue, the pH. Then you pinpoint the source. Is it the lungs or is it metabolic? From there, you follow the right investigative path, and you always check to see if the body's backup systems are working properly. And remember, if you've got a metabolic acidosis, the anion gap is your secret weapon to uncover the whole story. This whole framework, it just transforms a really complex problem into a series of simple questions. But, getting the diagnoses is really just the beginning, isn't it? The real question is, once you've figured out the precise nature of the problem, what do you do about it?